We invite you now to expand this window, to darken the room around you, and to prepare for a journey into one of the most haunting chapters in the history of human exploration. If you find yourself drawn to the deep questions of space, to the stories we've barely begun to tell, we gently ask that you subscribe. There will be more stories like this one, stories that demand time and silence and attention. What you are about to witness is not speculative. It is not fiction. It is the documented account of what happened when the Soviet Union turned its gaze toward the second planet from the Sun and what their machines found when they arrived. This is the story of Venus. This is the story of what we discovered there and why we have never returned. In the beginning, Venus was a mirror. It hung in the evening sky, brilliant and serene, the brightest object after the moon. Ancient peoples called it the morning star, the evening star, a goddess, a wanderer. It moved with a grace that suggested something fundamental, something tied to the rhythms of Earth itself. For millennia, it was little more than a point of light, beautiful and unreachable. But when humanity finally turned its telescopes toward it in the 17th century, something became immediately troublingly clear. Venus was hiding. The planet was wrapped in clouds. Thick, unbroken, impenetrable clouds that swallowed every wavelength of light humans could muster. No surface feature could be seen. No mountain, no ocean, no continent. Just white, endless white, reflecting more than 70% of the sunlight that touched it. And so Venus became not a world, but a question. What lay beneath those clouds? What kind of planet could generate such an atmosphere? Was it a jungle world, hot and wet, steaming under eternal overcast skies? Was it an ocean world, with vast seas swirling beneath the haze? Or was it something else entirely? In the early 20th century, as astronomers refined their understanding of planetary physics, Venus seemed poised to be Earth's twin. Its size was nearly identical. Its mass was nearly identical. Its distance from the Sun was closer, yes, but not impossibly so. It seemed reasonable, even likely, that beneath those clouds, conditions might be hospitable. The clouds themselves suggested water vapor. Water vapor suggested oceans. Oceans suggested life. This was the dream. This was the assumption that guided an entire generation of scientists and science fiction writers alike. Venus, in the popular imagination, became a swamp world, a prehistoric echo of Earth's own Carboniferous period, where giant ferns and strange reptiles might thrive beneath a thick, muggy sky. But the dream began to crack in the 1950s. Advances in radio astronomy allowed scientists to probe beneath the clouds using wavelengths of light that could penetrate where visible light could not. And what they found was heat, not the gentle warmth of a tropical planet, but a furnace. Radio emissions suggested surface temperatures far higher than boiling water. Some measurements hinted at values exceeding 400 degrees Celsius. This was impossible. This was absurd. How could a planet so similar to Earth, so close in size and composition, be an oven? The answer, when it finally arrived, would rewrite everything humanity thought it knew about planetary atmospheres. But that answer would not come easily. It would require machines. It would require sacrifice. And it would require the Soviet Union. By the time the space age began in earnest, the Cold War had transformed exploration into a proxy battlefield. Every satellite launched, every capsule sent into orbit, every human strapped to a rocket was a statement of ideology, a demonstration of technological supremacy. The United States and the Soviet Union were not merely exploring space. They were conquering it, claiming it, proving that their system, their philosophy, their way of life was the one that could master the cosmos. And in this contest, Venus became a prize. The Soviet Union had beaten the Americans into space with Sputnik. They had sent the first human, Yuri Gagarin, into orbit. They had achieved the first spacewalk. But the moon was slipping away. American resources, American focus, and the relentless momentum of the Apollo program made it clear that the moon would belong to the United States. And so the Soviets looked elsewhere. They looked to Venus. There were practical reasons for this choice. Venus, despite being a separate planet, is actually easier to reach than Mars in some respects. Its orbital alignment with Earth allows for launch windows that occur more frequently. The transit time is shorter. And most importantly, Venus was a mystery. If the Soviets could be the first to pierce its clouds, to land a machine on its surface, to transmit data back from another world, it would be a triumph that no moon landing could overshadow. It would be proof that Soviet engineering could go where no one else dared. But the engineers who designed the first Soviet probes had no idea what they were sending their machines into. They knew Venus was hot. They knew its atmosphere was thick. But the full, crushing, annihilating reality of that world had not yet been measured. And so the first attempts were built with optimism. They were built with the assumption that Venus might still, in some way, be a place where a machine could survive. The Venera program began in 1961. Only 4 years after Sputnik. The name itself, Venera, is the Russian word for Venus, and it would become synonymous with some of the most audacious engineering feats in the history of spaceflight. The first probe, Venera 1, was launched on February 12, 1961. It was a relatively simple machine by later standards, a cylindrical spacecraft weighing just over 600 kilograms, equipped with solar panels, a radio transmitter, and a handful of scientific instruments designed to measure magnetic fields, cosmic rays, and micrometeorite impacts during the long journey to Venus. The launch was flawless. The trajectory was accurate. For a brief, hopeful moment, it seemed as though the Soviet Union had achieved another first. But 7 days into the flight, contact was lost. The spacecraft's orientation system failed. Its solar panels drifted away from the sun. Its batteries drained. Its radio fell silent. Venera 1 continued onward, a dead hulk tumbling through the void. It passed within 100,000 kilometers of Venus on May 19, 1961, but by then it was nothing more than a ghost, unable to see, unable to speak, unable to fulfill the mission for which it had been built. The failure was devastating, but it was not unexpected. Spaceflight in the early 1960s was a brutal, unforgiving endeavor. Rockets exploded on launch pads. Capsules burned up in the atmosphere. Electronics failed in the cold vacuum of space. Every mission was a gamble, and the odds were rarely in favor of success. But the Soviets pressed on. Venera 2 and Venera 3 were launched in November of 1965, nearly 4 years after the first attempt. They were more sophisticated machines, heavier and more robust, designed not merely to fly past Venus, but to enter its atmosphere and, if possible, to reach its surface. Venera 2 was intended to conduct a flyby, passing close to the planet and gathering data as it swept past. Venera 3, on the other hand, carried an entry capsule, a spherical descent module built to withstand the heat and pressure of atmospheric entry. Venera 2 failed. Its telemetry system malfunctioned during the cruise phase, and by the time it reached Venus in February of 1966, it was blind and mute, unable to transmit the measurements it was designed to collect. But Venera 3 was different. On March 1st, 1966, its entry capsule plunged into the atmosphere of Venus. It became the first human-made object to reach the surface of another planet. But there was a problem. The communications system had failed before entry. The capsule descended in silence. It struck the surface somewhere in the vast, cloud-shrouded hemisphere of Venus, and humanity heard nothing. No data, no confirmation, only the cold, mathematical certainty that it had arrived. The engineers returned to their drawing boards. They refined their designs. They hardened their electronics. They thickened their heat shields. And in June of 1967, they launched Venera 4. Venera 4 was a revelation. It carried an entry capsule equipped with a parachute system, atmospheric sensors, thermometers, barometers, and a radio transmitter designed to broadcast its findings back to Earth as it descended. On October 18, 1967, the capsule separated from its carrier spacecraft and began its descent into the atmosphere of Venus. For 94 minutes, it transmitted. For 94 minutes, the world listened. What Venera 4 revealed was a planet utterly unlike anything humanity had imagined. The atmosphere was not water vapor. It was carbon dioxide, almost entirely carbon dioxide, more than 95%, with traces of nitrogen and sulfuric acid. The pressure was immense, far greater than anyone had predicted. At the altitude where the capsule's transmission ceased, the pressure had already reached 20 times that of Earth's atmosphere at sea level. The temperature had climbed to 260 degrees Celsius, and the capsule had not yet reached the surface. The engineers initially believed it had. The telemetry stopped, and the natural assumption was that Venera 4 had landed, that it had transmitted until its batteries failed or until the heat finally overwhelmed its circuits. But when the data was analyzed more carefully, when the descent rate was calculated and compared to the known radius of Venus, the truth became unavoidable. Venera 4 had been crushed. It had not landed. It had imploded somewhere high in the atmosphere, miles above the surface, destroyed by pressures that should not have existed. Venus was not a twin of Earth. It was not a jungle. It was not an ocean. It was hell. And the Soviets decided to go back. Understanding the scale of what the Soviet engineers faced requires understanding the environment they were designing for. Venus is not merely hot. It is not merely high pressure. It is a planet where the fundamental assumptions of engineering collapse. On Earth, we build machines with the understanding that air is relatively thin, that temperatures remain within a certain range, that materials will behave in predictable ways. On Venus, none of this holds. The atmospheric pressure at the surface of Venus is 92 times that of Earth. 92 times. To grasp what this means, imagine standing at sea level on Earth, where the weight of the entire atmosphere above you exerts a pressure of 1 bar, roughly 14.7 pounds per square inch. This is the pressure your body is adapted to, the pressure that every material, every seal, every electronic component is designed around. Now, imagine descending into the ocean. At a depth of 10 meters, the pressure doubles. At 100 meters, it is 11 times greater. At 900 meters, roughly the depth of the deepest freediving records, the pressure is 91 bars. This is the pressure at the surface of Venus. Not in its oceans, if it ever had oceans. Not in some deep trench. On its surface, standing on the ground. At this pressure, gases behave like liquids. The atmosphere is so dense that it exerts crushing, viscous forces on anything within it. A human being exposed to this environment would be compressed, their lungs collapsed, their body unable to expand against the weight pressing inward from all sides. But long before the pressure killed them, the heat would. The surface temperature on Venus is 467 degrees Celsius. This is hot enough to melt lead, hot enough to glow faintly in the infrared, hot enough that the rocks themselves are near their softening point, radiating heat like the coils of a stove. And this temperature is uniform. There is no night and day variation. There is no polar cooling. The thick atmosphere acts as a perfect insulator, trapping heat and redistributing it across the entire planet. Whether you stand at the equator or the pole, whether it is noon or midnight, the temperature remains constant, unwavering, lethal. The chemistry is no less hostile. The clouds that shroud Venus are not water. They are sulfuric acid, concentrated sulfuric acid, droplets of it suspended in the upper atmosphere, forming hazes and layers that scatter sunlight and give the planet its brilliant albedo. These clouds rain, but the rain never reaches the surface. The droplets evaporate in the searing heat of the lower atmosphere, creating a cycle of condensation and evaporation that has persisted for billions of years. Below the clouds, the atmosphere is relatively clear, but it is filled with trace compounds, sulfur dioxide, carbon monoxide, hydrogen chloride, each one corrosive, each one capable of degrading materials that would be considered durable on Earth. And yet, despite all of this, the Soviets believed they could build a machine that would survive. Not for years, not for months, but for minutes, long enough to transmit, long enough to see, long enough to answer the question, what is down there? The design philosophy that emerged was one of brutal pragmatism. Soviet engineers did not attempt to create a long-lived probe. They did not try to outsmart the environment or to find clever solutions that would allow delicate electronics to function indefinitely. Instead, they built machines that accepted their own destruction as inevitable. They hardened every component. They thickened every seal. They insulated every wire. And they designed the entire descent sequence around a single, narrow window of survivability. The entry capsules of the later Venera missions were spheres, roughly 1 meter in diameter, made of titanium. Titanium was chosen for its strength-to-weight ratio and its ability to withstand high temperatures without deforming. The sphere was pressure-tested to levels far exceeding what was expected because the engineers had learned from Venera that their predictions were always too optimistic. Inside the sphere, every instrument was mounted on shock-absorbing frameworks, isolated from the outer hull by layers of insulation. The electronics were solid-state, chosen for their resistance to heat and vibration. The batteries were oversized, providing enough power for several hours of operation, even though the mission would last only minutes. The radio transmitter was simple, robust, and capable of punching a signal through the thick atmosphere back to the orbiter overhead, which would relay it to Earth. The descent itself was a carefully choreographed sequence. The entry capsule would separate from its carrier spacecraft, while still hundreds of thousands of kilometers from Venus. It would coast for days, aiming for a precise entry angle that would allow it to bleed off velocity without burning up. As it struck the upper atmosphere, traveling at more than 11 kilometers per second, friction would heat the exterior to thousands of degrees. But the heat shield, a thick layer of ablative material, would char and vaporize, carrying the heat away and protecting the capsule within. Once the capsule slowed to subsonic speeds, a parachute would deploy. This was a critical moment. The parachute had to be strong enough to slow the capsule's descent, but not so large that it would tear apart in the dense atmosphere. The engineers experimented with multiple designs, eventually settling on a relatively small chute that would deploy high in the atmosphere and then detach partway down, allowing the capsule to free fall the rest of the way. This was not a flaw in the design. It was intentional. The lower atmosphere was so dense that aerodynamic drag alone was sufficient to slow the capsule to survivable impact speeds. The parachute was needed only for the upper layers. As the capsule descended, it would take measurements. Temperature, pressure, wind speed, chemical composition, light levels. Every sensor fed data to the onboard recorder, which in turn fed the transmitter. The signal was weak, corrupted by the static and interference of the ionized atmosphere. But it was enough. Ground stations on Earth, massive dishes trained on the sky, would capture the faint whisper of telemetry and reconstruct it, bit by bit, into knowledge. And then, if all went well, the capsule would reach the surface. It would strike the ground at a few meters per second, cushioned by a crushable shock absorber built into the base. For a few moments, perhaps as long as half an hour if the engineers had been lucky and thorough, it would continue to transmit. It would measure the composition of the soil. It would listen to the wind. It would take photographs if it carried a camera. And then the heat and pressure would find a weakness. A seal would fail. A circuit would short. The battery would drain. And the transmission would stop. This was the plan. This was the engineering philosophy that defined the Venera program. Not survival, but endurance. Not permanence, but presence. The goal was not to colonize Venus, or even to explore it in the way we explore Mars today, with rovers that drive for years across ancient lake beds. The goal was simply to be there for a moment and to tell the world what it was like. The next wave of missions began in 1969, less than 2 years after Venera 4's partial success. Venera 5 and Venera 6 were launched within days of each other in January of 1969. Both carried improved entry capsules, redesigned to withstand higher pressures based on the data returned by their predecessor. Both descended successfully. Both transmitted data from the atmosphere. And both were destroyed before reaching the surface. The readings they sent back were even more extreme than those from Venera 4. The pressure at the lowest altitude reached by Venera 5 was measured at 27 bars. The temperature was 320 degrees Celsius. And still, the capsules had not landed. The engineers revised their models once again. They realized that the surface pressure had to be even higher, perhaps 50 bars, perhaps more. The atmosphere was deeper than anyone had thought, denser than any simulation had predicted. Venus was not merely hostile. It was crushing. But there was something else in the data, something unexpected. As the capsules descended, their light sensors detected a peculiar dimming. The sunlight filtering through the clouds grew fainter with depth, but it did so in a way that suggested structure. The atmosphere was layered, with distinct regions of haze and clarity. The chemical sensors detected variations in composition, with concentrations of sulfur dioxide increasing at certain altitudes and decreasing at others. The wind measurements showed a powerful circulation, with speeds exceeding 100 meters per second in the upper atmosphere, a superrotation that carried the clouds around the entire planet in just 4 days, far faster than the planet itself rotated. Venus, it turned out, was not a static oven. It was a dynamic, churning, violently active world, with atmospheric processes unlike anything seen on Earth. And the Soviets wanted to know more. Venera 7 was launched on August 17, 1970. It was heavier than its predecessors, and its entry capsule was built to survive 180 bars of pressure, nearly twice what the engineers now believe the surface conditions to be. This was over-engineering by design, a buffer against the unknown. The capsule was tested in pressure chambers on Earth, subjected to temperatures and forces that simulated the descent as accurately as Soviet facilities could manage. On December 15, 1970, Venera 7 entered the atmosphere of Venus. The descent began normally. The parachute deployed. The sensors activated. Data flowed. But then, partway down, something went wrong. The parachute tore. The capsule began to fall faster than intended, tumbling as it dropped through the thick, hot air. The telemetry became erratic. Engineers monitoring the mission assumed the worst. But the capsule kept transmitting. It fell for 35 minutes, spinning, heating, the hull groaning under the mounting pressure. And then it hit. The impact was hard, far harder than designed, but the titanium sphere held. The shock absorber crumpled. The internal framework shifted. Several instruments failed, but the transmitter continued to broadcast. For 23 minutes, Venera 7 sat on the surface of Venus, transmitting a carrier signal back to the orbiter overhead. The data was minimal. The temperature reading was garbled, but suggested a value near 470 degrees Celsius. The pressure was estimated at 90 bars, though the sensor had been damaged in the impact. The signal was faint, drifting in and out as the atmosphere distorted the radio waves. But it was there. Venera 7 had landed. It had survived. Humanity had, for the first time, received a transmission from the surface of another planet. The achievement was profound, but the data was incomplete. The capsule had endured, but only barely, and much of what it was designed to measure had been lost in the chaos of the descent. The engineers knew they could do better. They knew they had to. Venera 8 followed in 1972. This time, the parachute system was reinforced. The entry profile was refined. The sensors were protected by additional shielding. On July 22, 1972, the capsule descended smoothly, transmitting continuously. It landed softly, exactly as designed. For 50 minutes, it sent data. Temperature, 470 degrees Celsius, confirmed. Pressure, 93 bars, confirmed. Light levels, detectable. This last measurement was a surprise. The engineers had assumed that the thick clouds would block nearly all sunlight, plunging the surface into near-total darkness. But Venera 8's photometer measured illumination equivalent to an overcast day on Earth. It was dim, yes, but not black. There was light. There was enough light to see. And so the next missions would carry cameras. The engineering challenges of photography on Venus were staggering. A camera designed for Earth relies on air cooling, on stable temperatures, on the assumption that lenses will not warp and that film or sensors will not degrade in seconds. None of this applied on Venus. The Soviets approached the problem with characteristic directness. They would not build a camera that could operate for hours. They would build a camera that could take one picture perhaps two, before the heat destroyed it. The cameras designed for the Venera landers were panoramic, using rotating mirrors to scan the landscape in a slow, sweeping arc. The optics were made of quartz, chosen for its high melting point. The mechanical components were lubricated with materials that could withstand extreme heat. The film, in the early designs, was replaced by a scanning system that transmitted the image line by line, pixel by pixel, back to Earth as it was captured. This meant that even if the camera failed partway through, some portion of the image would survive. Venera 9 and Venera 10 were launched in June of 1975. These were not merely entry capsules. They were orbital missions, each consisting of an orbiter and a lander, the first Soviet spacecraft to achieve orbit around another planet. The orbiters would serve as relay stations, capturing the transmissions from the landers and forwarding them to Earth, allowing for longer communication sessions and more detailed data. On October 22, 1975, the Venera 9 lander touched down on the slopes of a highland region. Its camera activated. The mirror began to rotate. And for the first time, humanity saw the surface of Venus. The image was black and white, grainy, and partial. The lens cap on one of the two cameras had failed to eject, so only half the panorama was visible. But what it showed was extraordinary. Rocks. Sharp, angular rocks, scattered across a relatively flat plain. The rocks were slab-like, some of them tilted at angles, suggesting that they had fractured and shifted over time. The lighting was diffuse, shadowless, coming from all directions as sunlight scattered through the dense atmosphere. The horizon was close, foreshortened by the curvature of the planet and the low vantage point of the camera. And the color, though the image was monochrome, was inferred from spectral measurements to be orange, a deep burnt orange, the result of sunlight filtered through sulfuric acid clouds. Venera 10 landed 3 days later on a smoother plane. Its camera also functioned, and this time both lens caps ejected successfully. The panorama showed a landscape of flat, pancake-like slabs fitting together like cobblestones. The surface appeared weathered, eroded, though by what process remained unclear. There was no water. There was no wind strong enough to move particles in the way wind erodes rocks on Earth. But the atmosphere itself, so dense and so hot, might be capable of chemical weathering, slowly dissolving and reshaping the stone over eons. Both landers transmitted for just over an hour before succumbing to the heat. But in that hour, they had done what no machine had done before. They had shown us another world, not as a point of light, not as a set of numbers, but as a place, a real, tangible, alien place. The Soviets did not stop. They could not stop. Venus had revealed too much, and yet still hidden more. The rocks, the temperature, the pressure, these were facts, but they raised deeper questions. What was the composition of those rocks? Were they volcanic? Sedimentary? How old were they? What do they tell us about the history of Venus, about its formation, about the processes that had turned it into the furnace it was now? Venera 11 and Venera 12, launched in 1978, carried a suite of instruments designed to analyze the atmosphere in unprecedented detail. Gas chromatographs, mass spectrometers, nephelometers to study the cloud layers, sensors to measure lightning and electromagnetic activity. Both landers successfully reached the surface and transmitted data, but both suffered camera failures. The lens caps, redesigned after the Venera 9 incident, failed again, this time refusing to eject at all. The missions returned atmospheric data, chemical profiles, and pressure readings of exquisite precision, but no images. The engineers were furious. Photography was not a luxury. It was essential. It was the one form of data that the public could understand, that could convey the reality of Venus in a way that numbers never would. The camera system was redesigned yet again. And in 1981, Venera 13 and Venera 14 were launched. Venera 13 landed on March 1, 1982. The camera activated immediately. Both lens caps ejected. The mirror rotated. And the image that came back was in color. Color. Not inferred, not reconstructed, but directly measured. The surface of Venus was orange, a rusty, sullen orange, the color of oxidized iron, the color of deserts on Earth, but deeper, more saturated. The rocks were jagged and sharp-edged, their surfaces textured in ways that suggested rapid cooling, volcanic origin. The sky was not black. It was not even dark. It was a murky yellow-orange, glowing faintly with scattered light, oppressive and claustrophobic. The lander also carried a drill, a mechanical arm designed to sample the soil and deposit it into an onboard X-ray fluorescence spectrometer. The drill bit into the surface, extracting a small core of material, and the spectrometer analyzed its elemental composition. The results indicated basalt, a volcanic rock rich in silica, magnesium, and iron, chemically similar to the basalts found on Earth and the Moon, but with subtle differences that suggested a more complex volcanic history. Venera 13 transmitted for 127 minutes, far longer than any previous lander. It measured wind speeds at the surface, a gentle breeze of less than 1 meter per second, almost nothing compared to the raging superrotation in the upper atmosphere. It recorded sound, using a microphone to capture the ambient noise of the Venusian environment. The recording was brief, distorted, but unmistakable. A low, rumbling hum, the sound of wind moving through dense air, the creak and groan of the cooling rocks, the faint hiss of the lander's own cooling system struggling against the heat. Venera 14 landed 4 days later and returned similar data. Its images showed a slightly different terrain, flatter, with larger slabs of rock and fewer small fragments. Its spectrometer measured a composition slightly lower in silica, suggesting a different volcanic source or a different stage of geological activity. It survived for 57 minutes. The two missions together provided the most complete picture of the Venusian surface that humanity has ever obtained. And yet, even this was only a glimpse, two tiny spots on a planet larger than continents, a world whose full story remained hidden. To understand why the data from these landers mattered, why the Soviet program poured so many resources into missions that lasted mere minutes, we must step back and consider the larger question. What is Venus? Before the Venera missions, Venus was a puzzle wrapped in assumptions. It was assumed to be Earth-like because it was Earth-sized. It was assumed to have oceans because it had clouds. It was assumed to be habitable because it occupied a region of the solar system that was not too hot, not too cold, within the so-called habitable zone where liquid water could exist. But every one of these assumptions was wrong, and the wrongness pointed to something deeper, something fundamental about how planets evolve. Venus and Earth are siblings. They formed at the same time, from the same disk of dust and gas that swirled around the young sun 4.5 billion years ago. They accreted from the same materials, rocky silicates, metals, volatiles, water, carbon. They grew to nearly the same size, Venus being about 95% the diameter of Earth and 80% the mass. Their internal structures are likely similar, with iron cores, silicate mantles, and thin crusts. In every measurable way that matters for planetary formation, Venus and Earth are twins. And yet one became a paradise, and the other became hell. The difference is the atmosphere. Earth's atmosphere is thin, nitrogen and oxygen, with traces of carbon dioxide, argon, and water vapor. It exerts a pressure of 1 bar at the surface and maintains temperatures that allow water to exist as a liquid. This is not an accident. It is the result of a delicate balance of processes, the outgassing of volatiles from the interior, the photosynthesis of early life, the weathering of rocks, the cycling of carbon between the atmosphere, the oceans, and the crust. Venus's atmosphere is the opposite. It is thick, almost entirely carbon dioxide, with pressures 90 times greater and temperatures hot enough to glow. There is no water. There are no oceans. There is no life. And the question that haunted scientists after the Venera missions was, why? What happened? If Venus started out like Earth, where did it go wrong? The answer lies in a process called the runaway greenhouse effect. Carbon dioxide is a greenhouse gas. It is transparent to visible light, but opaque to infrared radiation. When sunlight strikes a planet's surface, it warms the ground, and the ground radiates heat back into space as infrared. But if there is carbon dioxide in the atmosphere, the infrared is absorbed, trapping the heat and warming the planet. This is a normal, even necessary process. Earth's own atmosphere traps heat in this way, keeping the surface warm enough for liquid water to exist. Without the greenhouse effect, Earth would be a frozen ball of ice. But there is a threshold, a tipping point, beyond which the greenhouse effect becomes self-reinforcing. If the temperature rises too high, water begins to evaporate from the oceans. Water vapor is also a greenhouse gas, even more effective than carbon dioxide at trapping heat. As more water evaporates, the atmosphere traps more heat, which causes more water to evaporate, which traps more heat, and so on. This is the runaway. It is a positive feedback loop that, once triggered, cannot be stopped. On Earth, this threshold has never been crossed. The planet's distance from the sun, its rotation rate, its magnetic field, and the presence of oceans have all conspired to keep temperatures in check. But Venus is closer to the sun. It receives about twice as much solar energy per square meter as Earth. And at some point in its early history, likely within the first billion years, the temperature crossed the threshold. The oceans began to boil. Water vapor flooded the atmosphere. The greenhouse effect spiraled out of control. But water vapor alone could not produce the current conditions on Venus. Water vapor in the upper atmosphere would be broken apart by ultraviolet radiation from the sun, splitting into hydrogen and oxygen. The hydrogen, being light, would escape to space. The oxygen would react with rocks on the surface, oxidizing them. Over hundreds of millions of years, Venus should have lost its water entirely, leaving behind a dry but relatively moderate atmosphere. Instead, Venus is dominated by carbon dioxide, and this is where the second part of the story begins. On Earth, carbon dioxide is sequestered, locked away in rocks through a process called the carbonate-silicate cycle. Rainwater, slightly acidic from dissolved carbon dioxide, weathers silicate rocks, breaking them down and carrying the dissolved ions to the ocean. In the ocean, the ions combine with calcium to form calcium carbonate, which precipitates out as limestone. Over geologic time, this process removes carbon dioxide from the atmosphere, burying it in the crust. Meanwhile, volcanic activity releases carbon dioxide back into the atmosphere, completing the cycle. This cycle is a thermostat. If the planet gets too hot, the weathering rate increases, removing more carbon dioxide and cooling the planet. If the planet gets too cold, weathering slows, allowing volcanic outgassing to build up carbon dioxide and warm the planet. It is a feedback mechanism that has kept Earth's climate stable for billions of years. But the cycle requires liquid water. Without rain, there is no weathering. Without oceans, there is no place for carbonates to form. And once Venus lost its water, the cycle stopped. Carbon dioxide continued to outgas from the interior through volcanic eruptions, but there was no mechanism to remove it. It accumulated, and accumulated, and accumulated. The result is the atmosphere we see today. 93 bars of pressure, 467 degrees Celsius. A blanket of carbon dioxide so thick that it traps nearly all the heat radiating from the surface, creating a stable, uniform temperature that has persisted for billions of years. This is what the Venera missions discovered. Not just a hot planet, but a cautionary tale, a demonstration of how a world can transform, how a small difference in initial conditions can lead to radically different outcomes. Venus is not an alien planet in the sense of being exotic or unrelated to Earth. It is Earth's shadow, the version of our world that might have been if the dice had rolled differently. But the story does not end with the runaway greenhouse. The Venera data revealed another layer of mystery, one that still puzzles scientists today: Venus's geology. The surface imaged by the Venera landers is young. Not young in human terms, but young in geologic terms, likely less than 500 million years old. This is inferred from the density of impact craters, which are surprisingly few. Ancient surfaces, like the highlands of the Moon or the southern hemisphere of Mars, are saturated with craters, the accumulated scars of 4 billion years of bombardment. Venus's surface, by contrast, has only a modest number of craters, suggesting that something erased the older ones, resurfacing the planet in a relatively recent event. The leading hypothesis is global volcanism. At some point in Venus's past, perhaps 500 million years ago, the entire planet underwent a catastrophic episode of volcanic activity. Lava flooded the surface, burying the old crust beneath fresh flows. This would explain the basaltic composition measured by Venera 13 and 14, the sharp-edged rocks, the lack of weathering. But it raises another question. Why? What triggered such an event? And more troublingly, could it happen again? One possibility is that Venus's interior does not lose heat in the same way Earth's does. Earth has plate tectonics, a process where the crust is divided into rigid plates that move, collide, and subduct, carrying heat from the interior to the surface. Venus does not have plate tectonics, as far as we can tell. Its crust appears to be a single, unbroken shell. Without the constant release of heat through tectonic activity, heat builds up in the mantle, increasing pressure until it finds a release through volcanism. On Earth, this release is steady and gradual. On Venus, it may be periodic and violent, a cycle of buildup and catastrophic eruption that repeats every few 100 million years. If this hypothesis is correct, then Venus is not a dead world. It is a dormant one, waiting for the next eruption. And the implications for understanding planetary evolution are profound. It suggests that the interior dynamics of a planet, its ability to cool, to convect, to release heat, are just as important as its atmospheric composition in determining its fate. The Venera missions also detected another enigma: lightning. Multiple landers and atmospheric probes recorded electromagnetic signals consistent with lightning discharges, but the frequency and intensity were far greater than what is seen on Earth. On Earth, lightning is associated with water clouds, with the collision of ice crystals and water droplets that generate electrical charge. But Venus has no water clouds. Its clouds are sulfuric acid. How then does lightning form? One theory is that the lightning is volcanic, generated by the eruption of charged ash and gas from active volcanoes. Another theory is that the sulfuric acid clouds themselves can generate charge through turbulence and chemical reactions. The data from Venera is consistent with both possibilities, but it is not definitive. The landers were not equipped to pinpoint the source of the signals, only to detect their presence. The question of active volcanism on Venus remains unresolved. Orbital radar mapping missions, such as NASA's Magellan spacecraft in the 1990s, have identified thousands of volcanic features: lava domes, shield volcanoes, vast plains of solidified lava. But none of the images show direct evidence of ongoing eruptions. No fresh lava flows, no plumes of gas. The surface appears static, frozen in time. Yet the atmospheric chemistry, the presence of sulfur dioxide in concentrations that vary over time, suggests that something is still happening, that Venus is not entirely dormant. After Venera 14, the Soviet program shifted its focus. The landers had done what they were designed to do. They had measured the atmosphere, analyzed the rocks, photographed the surface, transmitted sound. The next step was to explore the planet more broadly, to map its surface, to understand its global structure. Venera 15 and Venera 16, launched in 1983, were orbital radar mappers. They carried synthetic aperture radar instruments capable of imaging the surface through the clouds, creating detailed topographic maps of the northern hemisphere. The data revealed vast highland plateaus, rift valleys, and impact craters, filling in the blank spaces on the map of Venus and providing the first comprehensive view of its geology. But the Soviet Union's resources were stretched thin. The Cold War was grinding on, the economy was stagnating, and the space program was being asked to do more with less. The Venera program continued, but the missions became less frequent, less ambitious. Venera 17 and 18 were planned as lander missions, but were never launched. The focus shifted to Venus-Halley missions, Vega 1 and Vega 2, which deployed balloons into the atmosphere of Venus before continuing on to intercept Halley's Comet in 1986. The balloons were an elegant solution to a difficult problem. A lander could only sample one location, a single point on a vast planet. A balloon, floating in the middle atmosphere, could drift for days, carried by the winds, measuring temperature, pressure, and chemical composition continuously as it moved. The Vega balloons floated at an altitude of 50 kilometers in the relatively benign environment above the sulfuric acid clouds. They transmitted for nearly 2 days, traveling thousands of kilometers, mapping wind patterns and atmospheric structure. But balloons could not see the surface. They could not drill into the soil. They could not photograph the rocks. And so, the most fundamental questions about Venus, the questions of geology, of history, of the processes that had shaped the planet, remained only partly answered. By the late 1980s, the Soviet Union was collapsing. The political will to fund grand space projects was evaporating. The engineers who had built the Venera missions were aging, their expertise scattered, their designs archived in dusty filing cabinets. The last Soviet mission to Venus, Vega 2, ended its transmission in June of 1986. And then, silence. Humanity has not returned to the surface of Venus since. In the decades that followed, other missions have visited Venus, but none have landed. NASA's Magellan spacecraft orbited from 1990 to 1994, using radar to map the entire planet with high resolution, revealing a world of tectonic deformation, volcanic plains, and mysterious coronae, circular features that may be the surface expressions of mantle plumes. The European Space Agency's Venus Express orbited from 2006 to 2014, studying the atmosphere and its dynamics, discovering that the superrotation is even more complex than the Venera data suggested, with waves, vortices, and transient structures in the clouds. But no lander, no rover, no camera on the ground. The reasons are practical. Venus is hard. It is expensive. The engineering challenges of building a machine that can survive on the surface, even for an hour, are immense. The scientific return, while valuable, is difficult to justify when the same resources could fund a Mars rover that operates for years or a telescope that peers into the distant universe. And there is a psychological barrier as well. Venus is hostile. It is uninhabitable. It offers no prospect of colonization, no dream of future settlement. It is a dead end, a world that teaches us what not to do, but offers no path forward. Yet the questions remain. What is Venus doing now? Is it volcanically active? Are there seismic events, Venus quakes, that could tell us about its interior structure? How does heat flow from the core to the surface? Why does the planet rotate so slowly, taking 243 Earth days to complete one rotation? And why does it rotate backwards in the opposite direction of its orbit? Did Venus ever have a magnetic field? And if so, what happened to it? The Venera missions provided answers, but they also revealed how much we do not know. The data they returned is still being analyzed, still being compared to models, still being reinterpreted in light of new theories and new observations. And as our understanding of exoplanets grows, as we discover worlds around other stars, some of them Earth-sized, some of them in the habitable zones of their stars, Venus becomes more relevant, not less. Because Venus is not unique. It is a type. It is a class of planet, a super-Venus or a mini-Venus, a world that started with the potential for life but took a different path. And if we want to understand how common life is in the universe, how fragile the conditions for habitability are, we need to understand Venus. We need to know what tipped the balance, what choices, what accidents of chemistry and physics led one twin to flourish and the other to die. The Soviet Union's Venera program was not merely a series of missions. It was a testament to a particular approach to exploration, one that valued endurance over elegance, function over form. The landers were not beautiful. They were not designed to inspire awe with their sleek lines or their sophisticated automation. They were blunt instruments, titanium spheres built to be crushed, cameras built to melt, batteries built to drain. But they worked. They reached the surface. They transmitted. They told us what Venus was like, not as we imagined it, but as it truly is. And what they found was a planet that should not exist. A planet where the atmosphere weighs as much as an ocean, where the temperature is hot enough to melt lead, where the clouds are made of acid and the rocks glow faintly in the dark. A planet where the wind whispers at the surface but roars in the sky, where lightning flashes in sulfuric acid storms, where volcanoes may still erupt, spewing gas and ash into an atmosphere already thick with poison. It is a planet that is utterly, absolutely hostile to life as we know it. And yet, it is also a planet that is hauntingly familiar. The rocks are basalt, the same material that forms the ocean floors on Earth. The carbon dioxide is the same gas that we exhale with every breath, the same gas that was once a major component of Earth's own atmosphere before life transformed it. The lightning, the wind, the clouds, all of these are processes that occur on Earth, twisted and amplified to nightmarish extremes. Venus is a mirror, and what it reflects is not our present, but our past and possibly our future. Because the runaway greenhouse effect is not a historical curiosity. It is a warning. Earth's atmosphere is changing. Carbon dioxide levels are rising, faster now than at any time in the past million years. The planet is warming. Ice sheets are melting. Weather patterns are shifting. And while Earth is not on the brink of becoming Venus, the mechanisms are the same. The physics is the same. The feedback loops, the tipping points, the potential for irreversible change, all of this is real. The Venera missions showed us what happens when a planet crosses the line. They showed us that small changes can have catastrophic consequences. They showed us that the conditions for life are fragile, contingent on a balance of factors that can be disrupted by forces both internal and external. But they also showed us that we can know. We can build machines. We can send them to other worlds. We can measure, analyze, and understand. We can look at Venus and see not just a dead planet, but a laboratory, a natural experiment in planetary evolution. And from that understanding, we can learn to protect our own world, to preserve the balance that keeps Earth habitable. The Soviet engineers who designed the Venera missions did not set out to save the world. They set out to explore, to compete, to push the boundaries of what was possible. But in doing so, they gave us something far more valuable than propaganda or prestige. They gave us knowledge. They gave us context. They gave us the ability to look at our own planet and understand how rare, how precious, how unlikely it is. The descent of a Venera lander was a brief event, measured in minutes. But the data it returned will last for centuries. The images, grainy and orange-tinted, will be studied by generations of scientists. The measurements of pressure and temperature will be refined and reinterpreted as our models improve. The sound recording, distorted and faint, will be enhanced and analyzed, not just as a scientific curiosity, but as the first audio ever captured on another planet, a reminder that these worlds are real, that they make noise, that they have a presence beyond the cold numbers in a database. And the silence that followed, the decades without a landing, is itself a kind of data. It tells us that Venus is hard. It tells us that the easy phase of exploration is over, that the low-hanging fruit has been picked. The next missions to Venus will not be simple. They will require new materials, new technologies, new approaches. They will need to operate for longer, to dig deeper, to see more. They will need to answer the questions that the Venera missions could not, questions about the interior, the history, the potential for life, not on the surface, but high in the clouds, where the temperature and pressure are more moderate, where liquid droplets might harbor microbes adapted to an acidic environment. These are speculative ideas, but they are not absurd. Life on Earth exists in extreme environments, in boiling hot springs, in acidic lakes, in the deep ocean where no sunlight penetrates. If life can adapt to such conditions on Earth, why not on Venus? The clouds are not as hostile as the surface. The temperature at 50 kilometers altitude is only about 60 degrees Celsius, warm but not lethal. The pressure is near 1 bar, the same as sea level on Earth. The sulfuric acid is a problem, but there are bacteria on Earth that thrive in acid. Could something similar exist on Venus, floating in the clouds, metabolizing sulfur compounds, reproducing in the mist? We do not know. The Venera missions did not carry instruments designed to detect life. They were built to measure chemistry, temperature, pressure, to photograph rocks, not to search for microbes. But future missions could. There are proposals, concepts, designs for atmospheric probes that would sample the clouds, looking for organic molecules, for chemical signatures that cannot be explained by abiotic processes. There are ideas for balloons that would float for months, drifting through different layers of the atmosphere, mapping the chemistry in 3 dimensions. But these missions are still on paper. They're still in the planning stages, waiting for funding, waiting for political will, waiting for the same kind of determination that drove the Soviet Union to send 20 missions to Venus over the course of 2 decades. And in the meantime, Venus waits. It rotates, slowly, backwards, its surface hidden beneath eternal clouds. The temperature remains constant. The pressure remains crushing. The wind continues its endless circulation, carrying sulfuric acid droplets around the planet in 4 days. The landers that reach the surface are still there. Venera 7, Venera 8, Venera 9, 10, 13, 14, all of them, their titanium spheres corroded, their circuits fused, their batteries drained, buried perhaps under drifts of fine dust, or half melted into the basalt. They are monuments, the only human artifacts on another planet aside from the Moon and Mars. And unlike the rovers on Mars, which may one day be retrieved, or the plaques on the Moon, which may one day be visited, the Venera landers will remain where they fell. No human will ever see them. No future mission will retrieve them. They are permanent as anything can be on a planet that erases its own surface every few 100 million years. But their legacy is not in the metal. It is in the data. It is in the understanding they gave us. It is in the realization that planets are not static, that they evolve, that they change, that they can die. And it is in the humbling recognition that we are lucky. Lucky to live on Earth. Lucky that the runaway greenhouse did not happen here. Lucky that the balance held, that the oceans remained liquid, that the carbon cycle continued, that life emerged and transformed the atmosphere and kept the planet stable for billions of years. Venus is a graveyard, but it is also a gift. It is a warning written in the language of physics and chemistry, a demonstration of what happens when the balance breaks. And the Soviets, with their blunt, pragmatic, relentless engineering, were the ones who read it for us. The missions they launched were not elegant. They were not poetic. They did not inspire the same awe as the moon landings, with their grainy footage of astronauts bounding across the lunar surface. But they were brave. They were ambitious. And they succeeded again and again in doing what everyone said was impossible. They built machines that landed on Hell. They built machines that transmitted from the surface of a planet where no machine should work. They built machines that lasted minutes, knowing that minutes was all they needed, that minutes was enough to change our understanding of the solar system. And now, decades later, as we look at Venus through telescopes, as we study its atmosphere with orbital probes, as we debate whether to return, we do so standing on the foundation they built. Every model of Venus's climate starts with the data from Venera. Every theory of its geology is constrained by the images from Venera. Every discussion of habitability, of runaway greenhouses, of the conditions necessary for life, references Venera. The program ended not because it failed, but because it succeeded. The Soviets answered the questions they set out to answer. They discovered what Venus was. And once they knew, there was no urgent need to return. The planet was not going to change on human timescales. The data was sufficient for the theories. The mystery was solved, or at least enough of it was solved that the remaining questions could wait. But waiting has a cost. Instruments improve. Techniques advance. The spectrometers we can build today are far more sensitive than those carried by Venera. The cameras are higher resolution. The drills can dig deeper. The computers can process data on board, selecting the most interesting samples, making decisions without waiting for commands from Earth. And the questions have evolved. We no longer ask simply what Venus is. We ask how it got that way. We ask whether it was always dead or whether it once had oceans, continents, perhaps even life. We ask whether we can see signs of that past in the rocks, in the isotope ratios, in the patterns of erosion. These questions cannot be answered from orbit. They require a lander. They require a rover. They require time on the surface, time to explore, to sample, to analyze. And time is the one thing that Venus does not give. The heat, the pressure, the corrosive atmosphere, all of it conspires to destroy machines within hours at best. The longest surviving lander, Venera 13, lasted just over 2 hours. Even with modern materials, with advanced insulation, with active cooling systems, it is hard to imagine extending that to days, let alone weeks. But there are ideas. Engineers have proposed landers built not to resist the environment, but to embrace it. Electronics that operate at high temperatures, using silicon carbide instead of silicon, capable of functioning at 500 degrees Celsius without cooling. Mechanical systems that use the heat differential between the lander and the atmosphere to generate power, eliminating the need for batteries. Sampling systems that operate on simple principles, using springs and levers instead of motors, reducing complexity and improving reliability. There are proposals for clockwork rovers, machines that do not use any electronics at all, that store energy in springs and release it slowly, creeping across the surface at centimeters per hour, navigating by mechanical logic. These ideas sound like science fiction, like a return to the Victorian era of mechanical computation, but they are serious proposals, grounded in the reality that sometimes the simplest solution is the most robust. And there are proposals for aerial platforms, gliders or airplanes that fly in the middle atmosphere, above the heat but below the clouds, mapping the surface with radar, sampling the air, looking for signs of volcanic activity. These would not land, but they would not need to. They would operate in an environment that is harsh but survivable, and they could cover vast distances, far more than any lander could. But none of these missions have been built. None have been funded. Venus remains on the back burner, a low priority in an era when Mars dominates planetary science, when the search for life focuses on the icy moons of Jupiter and Saturn, when telescopes are trained on exoplanets thousands of light years away. And yet Venus is right there. It is closer than Mars. It is larger than Mars. It is more Earth-like in size and composition than any other planet in the solar system. And it is a mystery that we have only begun to unravel. The Venera missions told us what Venus is, but they did not tell us why. They did not tell us when the oceans boiled away, or how long it took, or whether there was a moment when the planet could have been saved. They did not tell us whether life ever emerged, whether there were oceans teeming with microbes, whether there were continents, rivers, rain. They did not tell us what Venus looked like before it died. These are questions that matter, not just for Venus, but for Earth. Because the history of Venus is not ancient history. It is recent, geologically speaking, a catastrophe that unfolded within the last billion years, possibly even more recently. And if we can understand what triggered it, if we can identify the tipping point, the threshold beyond which recovery was impossible, then we can better understand the risks facing our own planet. Climate change is not a distant threat. It is not a problem for future generations to solve. It is happening now. The signs are everywhere, in the melting glaciers, the rising seas, the shifting weather patterns, the increasing frequency of extreme events. And while the greenhouse effect on Earth is not, at present, runaway, the mechanisms are the same. Carbon dioxide traps heat. Heat evaporates water. Water vapor traps more heat. The feedbacks are real. The physics is the same on Earth as it is on Venus. The difference is that we have a knowledge. We have the data from Venera. We have the models. We have the understanding to see the path ahead, to recognize the risks, to take action before the tipping point is reached. And that is the true legacy of the Venera program. Not the images, not the measurements, but the warning. Venus is what Earth could become. Not tomorrow, not in a century, but given enough time, enough carbon dioxide, enough disruption to the balance that keeps our planet habitable, Earth could follow the same path. The oceans could boil. The atmosphere could thicken. The temperature could rise until the surface glows. And once that process begins, once the feedbacks take hold, there is no stopping it. There is no reversing it. The planet becomes locked in a stable state, a hellish equilibrium that persists for billions of years. This is not speculation. This is not fear-mongering. This is the lesson of Venus, written in the rocks, in the atmosphere, in the measurements transmitted by Soviet landers before they melted into the surface. And so we return to the question that has haunted this entire story. Why have we not gone back? The answer is not simple. It is not that Venus is uninteresting. It is not that the science is unimportant. It is not that the engineering is impossible. The answer is that exploration is a choice, and choices are made based on priorities, resources, and vision. And in the decades since the Venera missions, the vision has shifted. The focus has turned to the search for life, and Venus, with its hellish surface and its sterile clouds, does not fit the narrative of a living universe. But that narrative is changing. Recent discoveries, measurements of phosphine gas in the clouds of Venus, controversial and debated but tantalizing, have reignited interest. Phosphine is a molecule that, on Earth, is primarily produced by biological processes. Its presence in the atmosphere of Venus, if confirmed, could suggest that something is living there, something we have not yet imagined, something that thrives in conditions we thought were impossible. The measurements are not definitive. They are contested. Some scientists argue that the signal is noise, that the data is ambiguous, that abiotic processes can explain the phosphine. Others argue that the presence of phosphine, even in trace amounts, is inexplicable without life. The debate is ongoing, unresolved, a reminder that Venus still has the power to surprise us. And so the proposals are being dusted off. The mission concepts are being revisited. NASA has selected 2 missions to Venus, Veritas and Da Vinci Plus, scheduled for launch in the late 2020s. The European Space Agency is planning Envision, another orbiter, for a similar time frame. These missions will not land, not in the way Venera did, but they will probe the atmosphere, map the surface with unprecedented precision, search for signs of active volcanism, and try to answer the questions that have lingered since the Soviet era. But they are not Venera. They are not landers. They will not touch the surface. They will not drill into the rocks. They will not photograph the terrain in color. They will not record the sound of the wind. And so the most visceral, the most direct connection to Venus, the experience of being there, even if only through the eyes of a machine, remains locked in the past, in the grainy images and faint radio signals transmitted by Soviet probes decades ago. And perhaps that is fitting. Perhaps the Venera missions represent a moment in history, a time when exploration was driven not by careful calculation of scientific return, but by ambition, by competition, by the simple desire to go and see. The Soviet engineers did not ask whether a lander that lasted 2 hours was worth the cost. They asked whether they could build it. And when the answer was yes, they built it. There is a purity to that approach, a directness that is rare in modern space exploration, where every mission must justify itself with detailed science cases, with cost-benefit analyses, with comparisons to alternative uses of the same resources. The Venera missions were not justified in this way. They were justified by the fact that Venus was there, and we did not know what it was like, and the only way to find out was to send a machine to the surface and see. And so they did. 20 missions over 2 decades, a relentless, grinding campaign of trial and error, of failure and success, of machines that were crushed, melted, and silenced, but that one by one, piece by piece, revealed the truth about Venus. The truth is that Venus is hell. But it is a hell of our own making, in the sense that we, as a species, have the power to create the same conditions on Earth. The runaway greenhouse effect is not inevitable. It is not a law of nature that all Earth-sized planets must become Venuses. It is a contingency, a path that is taken only if certain conditions are met, if certain thresholds are crossed. And the Venera missions showed us where those thresholds are. They showed us what happens when carbon dioxide accumulates unchecked. They showed us what happens when the oceans boil away. They showed us what happens when the feedback loops take hold. This is the knowledge we carry now. This is the burden and the gift of exploration. We know what Venus is. We know what it could have been. And we know, with uncomfortable clarity, that the difference between Earth and Venus is not as large as we would like to believe. The Soviet Union is gone. The engineers who built the Venera missions are aging or have passed away. The factories that constructed the landers have been repurposed or demolished. The infrastructure that supported the program, the tracking stations, the mission control centers, the vast network of expertise and institutional knowledge has dispersed. But the data remains. The images remain. The measurements remain. And the lessons remain. Venus is a graveyard, but it is also a classroom. It is a place where the laws of physics play out in their most extreme form, where the consequences of small changes are amplified to planetary scale. It is a place that teaches us humility, that reminds us that the conditions for life are fragile, that the balance can tip, that there is no guarantee that Earth will remain habitable forever. And it is a place that the Soviets explored with machines that should not have worked, that lasted minutes when they should have lasted seconds, that transmitted images when they should have melted, that survived long enough to tell us what we needed to know. The story of Venus is not over. The planet continues to evolve, to churn, to radiate heat into space. The clouds continue to swirl. The wind continues to blow. The surface continues to glow. And somewhere, buried in the dust, the Venera landers rest, their missions complete, their messages sent, their place in history secure. We will return to Venus. Perhaps not soon. Perhaps not in this decade or the next. But eventually, the questions will demand answers that can only be found on the surface. The technology will improve. The materials will advance. The political will, or the scientific curiosity, or the simple human desire to explore will reassert itself. And when that happens, when the next lander descends through the sulfuric acid clouds, when the next camera activates and begins to transmit, when the next drill bites into the basalt, we will do so standing on the shoulders of the Venera program. We will remember that the Soviets went first, that they endured failure after failure, that they rebuilt and redesigned and tried again, that they succeeded where others said success was impossible. And we will remember that what they found was not a paradise, not a garden, not a world waiting to be colonized, but a warning. Venus is the planet that died, is the twin that took the wrong path, the mirror that shows us what we must avoid. And the machines that landed there, that survived for minutes in an environment that destroys everything, are monuments not just to Soviet engineering, but to human determination, to the refusal to accept ignorance, to the insistence that we must know, even if what we learn is terrible. The story of Venus is the story of a planet that lost its balance, that crossed a threshold from which there is no return. It is a story told in heat and pressure, in rocks and clouds, in the measurements transmitted by dying machines. It is a story that the Venera program spent 2 decades uncovering piece by piece, mission by mission, until the truth was undeniable. And the truth is this: Venus is a cautionary tale. It is a reminder that planets are not eternal, that the conditions for life are contingent, that the balance can be lost. It is a reminder that we are not immune, that Earth is not guaranteed, that the decisions we make now will echo through geological time. The Soviets found hell on Venus, but in finding it, they gave us something invaluable. They gave us context. They gave us perspective. They gave us the knowledge to recognize the danger, and with it, the possibility of avoiding the same fate. Venus is the second planet from the Sun, Earth's twin in size, a world that should have been like ours. But it is not. It is a furnace, a pressure cooker, a planet where machines survive for minutes and the temperature melts lead. It is a planet that we have visited briefly, with machines built to be destroyed, and from which we have learned more than we ever imagined. This is what the Soviets found on Venus. This is the story of the Venera missions. This is the legacy of the engineers who built landers that should not have worked, who sent them into an environment that should have been impossible, and who, through sheer determination and relentless iteration, succeeded in showing us another world. The images are grainy. The data is sparse. The missions lasted minutes, but the impact is eternal. Because what the Venera missions discovered was not just a planet. It was a lesson, a warning, a mirror, and we would do well to remember it. The screen fades to black. The music swells briefly, then falls to silence. In the darkness, a single line of text appears. The Venera landers remain on Venus, corroded and silent, the only evidence that humanity once dared to visit hell.